Hi, everyone. It's nice to see so many of you here on Zoom. And I'd like to begin by thanking the organizing committee for putting together this interesting symposium and for the opportunity of being here today. And I will talk about technosignatures in the context of direct imaging of exoplanets. And in particular, I will talk about something that we call starshades. And that is large-scale structures that we think might be detectable with near future technology. Okay, so before I begin, I would also like to introduce myself a bit more. My name is Claudia, and I am currently a PhD student in the supernovae group at Stockholm University in Sweden. So I typically work on peculiar supernovae and observations of them with the aim to decipher their origins. However, about 3 years ago, I did my bachelor thesis project on technosignatures. And this is what led to the research that I will talk about today. So last year, I published my first paper in the monthly notices of the Royal Astronomical Society, together with Alexander Mustel, who was my supervisor for my bachelor's project. And yes, so I will not talk about supernovae today. I will explain why and how technosignatures in the form of starshades could be detectable with near future technology. Okay, as we have seen, technosignatures can take form in various different ways. We can see them as electromagnetic signals, atmospheric pollution, or as large-scale technological structures, which is what I will talk about today. And starshades in particular can be said to be a type of shield that shields out starlight from a star to maintain a certain temperature on an orbiting planet. So it reduces the radiation received by the planet and maintains the planet habitable with time. And the reason for this is that all stars, as they evolve on the main sequence, experience an increase in luminosity as they age. And to visualize this, I have included a habitable zone evolution plot here of the solar system. I have also included the planets Mars, Earth, and Venus for comparison. And as you can see, we have time on the x-axis and then the distance, habitable zone distances on the y-axis. And as the sun evolves, these distances move further and further away from the star. So even though we talk about very large timescales here, the Earth will eventually be placed outside the habitable zone. And this is true for all stars on the main sequence that we might think have planets that host life out there. So that is why this is an interesting thing and why starshades could actually be something that extraterrestrial civilizations use to solve this problem. And as the habitable zone distances increase with time, so does the necessary starshade size necessary to deflect away enough radiation to maintain a certain temperature on an orbiting planet. So you see an example of this here. To the left, we have the habitable zone evolution again, and then we have the starshade radius as a function of time. So say after many mega years, so we're talking about large timescales here again, but we see that eventually such starshade would have to be of similar size to the orbiting planet. And that would mean that we would see very large scale structures. And this is actually something that has been researched before, mainly by Eric Gaidos in 2017, who showed what these structures would look like in transit light curves. And you see an example here to the right, what it would look like in a transit light curve. And the noticeable thing here is that we see an increase in light as the star shade is occulted by the planet when it moves in front of its host star. So it clearly looks different to what we expect a normal planet to look like. And that's pretty interesting. But since it has been researched in transit light curves before, what we wanted to do was to look into another exoplanet detection technique. And there are several of those. You see some examples here where we see the planet mass versus orbital distance for detected exoplanets with various methods. And today I will talk about direct imaging. And that is the planets in the upper right region of this plot. You also see planets of the solar system included in this plot. So we have Venus and Earth in the very bottom, and the other planets are, of course, larger and at a larger orbital distance. So the problem with direct imaging here, of course, is that previously it has been limited to very large planets at large distances to the host star, and that is not where we expect a habitable zone to be. And we are looking for planets, ideally, that are similar size to Earth. However, the upcoming Habitable Worlds Observatory is planning to be able to detect Earth-sized planets in the habitable zone, as you see indicated in this plot here. So in the future, this could actually be very much possible to directly image Earth-sized planet in the habitable zone. And this is an example image of a direct image of a 4-planet system. And as you can see, what we need to do when we do direct imaging is we need a way to block out or filter out the light of the star in order to see the much fainter planets around it. And this has been a part of the issue why we cannot see small planets in close orbit to the star. But the technology is improving, and hopefully that is what we will see very soon. And before I move on to what it will look like if we had a star shade in direct imaging, I want to just walk through some assumptions we made during our study. So we assume a perfectly flat circular disk placed at the inner Lagrange point between the star and the planet. We assume a starshade albedo of 0.9, so it's a very highly reflective structure, and a planet albedo of 0.4. So this will affect how the system appears in direct imaging. We also place the hypothetical planet at an Earth equivalent distance, and that is the distance at which the planet would receive the same amount of light as the Earth do from the sun. And it would look something like this in this plot with the star shade, and the planet. However, when we do direct imaging, we don't resolve the planet completely, but instead what we can do is construct a phase curve which shows the total reflected light towards the observer as a function of where the planet is in its orbit. And this is something for planets that we use the model from Heng and collaborators from 2021 to construct the typical planet phase curve. And it looks something like this. However, for a star shade, we would expect something completely different. Since the star shade is a disk, and we expect one side to be reflecting away starlight and the other side to be essentially not reflecting any light, it would look something like this. So we see an increase in light as the reflective side is facing the observer, and no light as the non-reflective side is facing the observer. However, as I said, we cannot resolve the planet itself, and we don't expect to be able to resolve the Lagrange point distance as well, which means that we would see a contribution from both the star shade and the planet together, and that would look something like this. So here I want you to look at the most amplified curve, which is the star shade plus the planet, and then I have also plotted a normal planet for comparison here. So still, even though we have to combine these two, we see that we have a very different shape of the phase curve than what we would expect from a typical planet. Not only is it very amplified, it also has a very sharp edge. or around the edges when we see the backside of the star shade and it doesn't reflect any light. So it looks very different to what we would expect. And then one could guess that this would maybe be something that we can actually detect. So in order to see or also like quantify how detectable such signatures would be, we applied our concept to the Habitable Worlds Observatory that I briefly mentioned before. And here also an important point is that the telescope blocks out the light from the star. So we have an inner working angle that, depending on how large it is, we will see different amounts of the phase curve, which is also visualized in the plot here. So the Habitable Worlds Observatory is planned to launch around year 2040, and it will search for Earth-like planets in the habitable zones. The inner working angle is not yet set, as far as I know, and is still under discussion. So therefore, we have used two different inner working angles in our analysis to see what difference it makes for the results. And here is an HR diagram for the star shade candidate stars among the HWO sample. So here I have plotted all of the HWO target stars from a target list by Harada and collaborators from 2024. And we have excluded some of the stars from our sample with the condition that they have to be older than 1.5 gigayears. This has mainly two reasons. First of all, we want the star shade size to be, we want it to be big enough to be able to detect it. And also life on Earth, we think took around 3.5 gigayears to develop. So it doesn't really make sense, since we only have one data point for life, to take the very, very young stars. Yes. So just a short outline of our method. We first find the stellar age of all of our stars by isochrone fitting based on the luminosity and effective temperature. And then we assume the star shade is built at different starting ages, since we cannot really assume anything about when a civilization would need to build such structure. Then we place the planet at the Earth equivalent distance, and we simulate the star shade size up until the current stellar age. And then we generate phase curves for all of our systems at current stellar age. And in order to quantify the results, we determine the maximum difference between our phase curves and the curve of a typical planet. And what I mean by that is this. So we take the difference of our very amplified star shade plus shaded planet curve, and then minus that what we would expect for just a typical planet. And here, the dashed line that's saying shaded planet, that is because what we actually take is a planet that it has been that has less radiation than we would expect. So it reflects a bit less light since it has this shield in front of it. So we take the shaded planet plus the star shade phase curve to construct the total one. So let's look at an example simulation for one of our stars. Here we assume a star shade size of 0.8 Earth radii. So it's a very large scale star shade. And then it would look something like this. So once again, the most important curve here is the most amplified one. And once again, we expect a very different shape, a very amplified curve for our star shade planet system. Also important here is if we change the inner working angle, here we have an inner working angle of 45 milliarc seconds. If we increase it to 60, it would look something like this. And this shows the importance of having as small inner working angle as possible when we observe planets in close orbit with a star in the habitable zone. So in the end, we simulated up to 500 phase curves for each star in our sample. And that is for different starting ages, so different ages for when the civilization built the starshade, and also 100 randomly drawn inclinations for each of the star. So up to 500 simulations per star. And then we averaged the delta max for each star in our sample. So there were a lot of simulations going into this. And then the results look something like this. And the important part in these plots is the red line that you see, the red horizontal line. We want ideally all of the stars to be above this one, since that would mean that we would get a technosignature that is above, or a delta max that is above the precision of the telescope. So for 45 milliarc seconds, almost all of the stars are above this line. It's around 96% of the stars. But for the 60 milliarc seconds in a working angle, only around 70% of the stars are above this line, and also some of them are very close, so it would be more difficult to distinguish the technosignature of a starshade. And before I end this talk, I would like to say a few words to conclude. So starshades can be used to maintain habitability as a star ages. And we do expect such structure or similar reflective structures to have very distinct shapes when it comes to phase curves. So it is something that we should look out for. And a smaller inner working angle, of course, increases the possibility of detecting such structures. And lastly, with an inner working angle of 45 milliarc seconds, our results show that the average phase curve signature of a starshade lie above the 1 sigma limit of the HWO telescope for around 96.7% of the targets. And I will leave this slide here, and that was all I had prepared for today, but let me know if you have any questions, and thank you for your attention.
Thank you so much, Claudia. Yes, very interesting. So we have maybe time now for one question, but then later, after the talk, we have a discussion time for the questions. So let's start from the first I've said. Is there anything that might look like a star shade in a phase curve, but wouldn't be? For example, stellar activity.
Regarding stellar activity...
sorry, I want to say it's from Diana Solana Oropesa.
Yes. Regarding stellar activity, I'm not sure, but what we have looked and compared our curves to briefly are moons, planetary rings. I've also had a look at how different types of clouds would look like in phase curves. And when it comes to ring structures and moons, it doesn't really look like anything similar to this. However, clouds can sometimes, they are a bit more tricky because they can sometimes mimic these structures. If you, for instance, have a cloud or a polar ice cap at some part of the planet, so you get a very sharp signature in the phase curve, so to say. So that is something that we need to be careful about, but it's mainly clouds that I have seen can produce similar things.
Okay, thank you. Maybe to clarify also one question from Valentin Ivanov. He's asking about the cost for HWO Starshade, implying that the operational cost will be larger. But I think your talk is not about that, not Starshade for HWO. It's for searching starshades or around other planets.
Yes, exactly. I think they will use a coronagraph to block out the stellar light from the systems with HWO.
Yes.
But I have no idea about the costs.
Yes, I think so too. Yes, just to clarify that this is not using starshades at HWO. All right, thanks a lot. We move to another talk. Please stay with us. We will have a discussion session. We keep questions for discussion questions session. There are several for you.
Yes.
All right.
Thank you very much.
Applause, virtual applause. Thank you very much.